Today I'm going to talk about a variation of adiabatic quantum computing in which instead of encoding the information over regular qubit, we just encode the information over an ensemble of qubits. I was doing this project in a group in a campus of New York University campus in Shanghai with these guys. So I would like to start with a brief introduction of quantum computing models, and as one of quantum computing models, I will talk a bit about adiabatic quantum computing, and then I will talk a bit about quantum computing using an ensemble of qubits, and then finally I'm able to introduce our main proposal, which is somehow combination of these two models, adiabatic quantum computing models and quantum computing using ensemble of qubits. So you know better than me, there are a few universal quantum computing models which are working either based on discrete time evolutions or either based on continuous time evolutions. I'm not going to talk about the third one, but as a brief introduction for the first one and the second one, I would say in the gate model, you know that we just initially prefer our qubits in some initial states, and then we apply some Hadamard gates, and then we apply sequences of unitary transformation, and then finally we have the desired state that we are looking for. But what is important in the gate model is that we are able to manipulate and control the evolution of and control the state during the evolution. But it makes it a bit technically difficult to get all the qubits to work together coherently, and the state of the art for the gate model is just about a few 10 qubits. So then maybe quantum computing models based on continuous evolution offer some alternative way for doing quantum computing, which one of them is adiabatic quantum computing. What is important and interesting in adiabatic quantum computing is that we don't need to have any control over the system. Actually, we have no control over the system during the evolution. We just set up the system in some initial state and then let system to evolve by its nature, and then finally system ends up in some final state, which is the state that we are looking for. And the state of the art for quantum computing, for adiabatic models, is about a few thousand qubits, like what we now we have with E-wave. So quantum computing models are supposed to be useful for the problem that are hard to be solved with the classical computers. And as most of you know, one of class of problem which is hard to be solved with the classical computer is optimization problems, that we're going to find one optimum solution between many possible solutions. So just to have some idea why these problems are such hard to be solved with the classical computer, let me to give this simple example. So just suppose we're going to order 10 people around the table, how many configuration is able to order these people around the table is 10 factorial, which is a very big number. Now suppose we want to add every time one guy to the number of people that we want to order around the table, and you can see that the number of configuration scales exponentially with the number of people that we want to order. So this is what makes it hard to be solved with the classical computer, because you should just be able to go through all the possible configurations to find that configuration that you are looking for. This is one class of problem which is hard to be solved with the classical computers. But there are some other class of problems which are hard to be solved with the classical computers. But all what these problems have in common is this exponential scaling with the size of the problem. So one idea for solving the optimization problems comes from a fundamental rules in physics, that any physical system tends to be in its lowest energy state. So then this suggests this idea that, okay, you can just map any optimization problem in a physical system and then let system evolves to its ground state and then we have the solution. But just the original idea of using a physical system to find the optimal solution, and it comes back to this paper, and just to have some idea that how much this problem is of interest, as you can see how many citations this paper has. And this is the original paper that introduced the connection between optimization problem and the thermal equilibrium behavior of systems that have so many degrees of freedom. So then people thought that, okay, it's good that we can map any problem on a physical system in a way that the ground state of the system offers the solution that we are looking for. And then one step further, they said, okay, maybe there are some resources in quantum mechanics that helps to improve this type of searching, which is quantum tunneling and entanglement. So this is what here is where the quantum annulings come to play a role, and to see how adiabatic quantum computing models can offer some ways to solve the optimization problems. So then I prefer here to just a little bit talk about adiabatic computing model, and then I will introduce our proposals. But I think most of you know that this is the general formula for any adiabatic evolution, and the system will start from some initial state, and then Hamiltonian gradually evolves to some problem Hamiltonian and final Hamiltonian. That the ground state of the problem Hamiltonian or final Hamiltonian is the solution that we are looking for. So this evolution, if the evolution would be enough slowly, then it always guarantees that the state of the system always can be found in the ground state, so that at the end of the evolution, we comes up with the ground state of the problem Hamiltonian, which encodes our solution, what we are looking for. So here you can see the eigenspectrum for some typical adiabatic Hamiltonian. You can see there is some point that the ground state approaches to the first excited state and then it diverges. So we can guarantee that the system always will be fine in its ground state just if the time evolution would be larger than 1 over the square of this minimum gap. But different problem Hamiltonians have different structure, different spectrum. Some of them are easiest and some of them are hardest. The easiest one are that one that have large gap, and the smallest one are that one that has a small gap. But there is one issue with AQC, and the issue is that the minimum gap is an unknown prior, and it's not possible to make a general statement for the gap. So this motivates us to propose some method that I will talk about it in a few slides. Just have in your mind this problem with AQC. So now I would like to talk a bit quite briefly about ensemble quantum computing. In this model, for encoding the information, we use an ensemble of qubits instead of one single qubit. If we want to encode the information corresponding to this qubit, we encode the information in this way on a spin coherent state, which as you can see, it's like that we store the information in a highly duplicated way. So it offers kind of robust storage of quantum information. If during the evolution you lose one or a few qubits, it doesn't cause to a big error. So, but this using ensemble for computing is interesting because it can offer the possibility of observing quantum effects in microscopic scales, and this is why it's interesting. But there is a big problem, and one can argue that, okay, when you use ensemble, when you use microscopic system, then the coherency will destroy everything. So, but there is a solution for that. You know that the coherency is a state-dependent process. So if we find some a smart way for encoding, then we can somehow circumvent this problem, as I show you in our proposal in a few minutes. Okay, now I have all ingredients to introduce our main proposal. If you don't have any question, I can continue. Just feel free to stop me in any point that you have any question. Okay, here you can see again the general. I want to use quantum computing based on ensemble for AQC. So here you can see the general formula of AQC for any adiabatic evolution. A rather general choice for initial Hamiltonian and problem Hamiltonian is has such form. Which with this form, we are able to encode a variety of optimization problem. So now the first step, we should somehow write the ensemble version of this adiabatic Hamiltonian, but we should write the ensemble version in a way that it fulfills some criteria that we are looking for. For example, this ensemble version should be so that it somehow preserve the gap still, because you know when we have an ensemble, then maybe the gap starts to close it. So then the mapping should be so that it preserve the gap. So we found that we can write the ensemble version of this Hamiltonian in this way. And as you can see, we just substituted the Pauli operators with total spin operators. And the other difference is that there is a factor of 1 over in front of two-body ensemble interactions. So here just let me to emphasize that I have two parameters that I am working with it during this talk, M and N. So just keep in your mind that N here is ensemble size, that means number of particles that I have in each ensemble, and M is number of qubits. Okay, so now we have the ensemble version of the our adiabatic Hamiltonian. But why this ensemble version could be interesting? I will list here a few of properties of this mapping, and then later on you can see all these properties. So the first one, as you remember, I told you that one big problem with AQC is that it's not easy to make a general statement for the gap, and you cannot estimate the gap already. But this ensemble nature of this proposal that I want to tell you give us this possibility that we use mean field and we just estimate the gap for I just emphasize just for some particular problems. And as a second advantage of this mapping, I would say that ensemble formulation offers some type of error suppression, that this error suppression comes somehow from the duplication of encoding that I explained you in a few slides ago. So, and then finally, I would say that as you saw in the formula, in the adiabatic formula, you have seen that it appears just the spin total operators. This means that we don't need to individually control all the qubits in the system. So then it makes it even experimentally to be not to, it would not be so hard to be implemented in the lab. So, but we should answer two main questions under this mapping. Okay, the first question, how the ground state of this qubit version and ensemble version are related together? And as a second question, how the gap of qubit version and ensemble version are related together? So let me first look at the first question. So here again, you can see the qubit version of the problem Hamiltonian and ensemble version. So just keep in your mind, here I'm talking just about the problem Hamiltonian, not the whole adiabatic Hamiltonian. So, the eigenvalue, S-set operator, Pauli operator have the eigenvalue of -1 and +1. But in this mapping, under this mapping, the total spin operator can have these values for the eigenvalues. So now if I define a new variable in this way, then you can see that xi can have values between -1 and 1. But you should be careful that it has discrete values between -1 and 1. Now, if you just compare these ensemble version with the qubit version, you can see that for the extremal values of -1 and 1, this ensemble version reduces to this qubit version up to a factor of n. Okay, then this suggests that the primary difference between ensemble version and qubit version is that for the ensemble version, xi can take some discrete set of intermediate value between -1 and 1. To understand this a bit better, just here I plot the landscape of the energy for both of qubit version and ensemble version. So here you can see some dots. Dots here shows the allowed state for both of qubit and ensemble version. So you can see for the qubit version, xi just allowed to have the value of -1 and +1. So the allowed states are just the corner of this hypercube. So, but this is not the case for the ensemble version. And we have some intermediate value. So these plots are for these typical for these parameters of the problem Hamiltonians. So now we want to know what is the relation between the ground state of the ensemble version and the ground state of the qubit version. For the qubit version, we know that it's always in the corner of hypercube. But whether we can make this claim that the ground state of the ensemble version is always in the corner of the hypercube or not. So then we just study the variation of the energy from some corner, which is the ground state, to other corner of the hypercubes. I am showing the result here for some particular instance, but we have shown this that this would be generally true that any point from ground state from a corner, which is the ground state, to other corners always has a positive slope. That means the ground state always is in the corner of the hypercube. And this means that we can say that the ground state of the qubit version and ensemble version have a kind of logically equivalent spin configuration in this sense. This relation says that all the first few excited state for the ensemble version, that expectation value of spin operators have the same sign with the expectation value of Pauli operators. They are logically equivalent with the ground state. So if just to understand this better, here I plotted the spin configuration for a 2-qubit system. Here, this is the qubit version that we have just one particle in, and here is for like an ensemble version with 3 particles in each qubit. So this shows the configurations for first qubit, and this shows the configuration for the second qubit. This is the first energy level, this is the second energy level, and so on. So here you can see this is the ground state of this particular problem. First spin up and the second spin down. So the expectation value of the Pauli operator is here 1 and -1. Now if you look at the expectation value of spin Pauli total spin operators in the ensemble version, we can see the two first excited state here have the same sign with the qubit version. So that means these states are still equivalent with the ground state. And this is what is called and what is known as majority vote coding. So now we somehow know how the gap, how the ground state of the ensemble version and qubit version are related together. So is there any question? So now I go through the second question. Okay, how the gap of ensemble version and qubit version are related together. So here you can see this is the ground state. This is for the qubit version. This is the ground state, and this is the first excited state for this particular problem that I plotted here, the landscape. So then it's clear that the gap is just difference between the energy of the ground and the first excited state. Now, if I just calculate the corresponding, the difference energy between corresponding corners for the ensemble version, is just the difference energy for the qubit version multiplied by n. But could it be the gap really for the ensemble version? So you see, here there is a factor of n, and then when n is enough large, it makes it to be somehow less likely that this would be gap, because it becomes at some point it becomes very large. So then this suggests that maybe the the first excited state could be just a single spin flip of the ground state. But if we just define the first excited state as a single qubit spin flip of the ground state, we can see the gap has such definition. Here, these are just the parameters of the problem Hamiltonian, and sigma here shows the sign of the expectation value of total spin operators. Okay, so I have two definitions for the gap. The first one is that offers that for the ensemble version, the gap is just the gap of qubit version multiply n, and this one, this small delta, says that the gap is just a single spin flip of the ground state. Now, how we can realize whether this small delta is the gap or whether this big delta is the gap? So, as I mentioned, this linearly grows with n, but while this has nothing to do with n, so there should be always a crossover between this and this. So let's call the point for the n that it happens a crossover between this and this. Let's call it critical n. So if we consider an ensemble with n, which n is smaller than this critical number, then always this delta is smaller than this delta. That means the gap for the ensemble is really this gap, which is just the gap for the qubit version multiplied by n. But if the number of particles in ensemble is larger than this critical point that crossover between this and this happens, then capital delta is larger than a small delta, and this would be the gap of the ensemble version, which is just the spin flip. I just mentioned it again. This says that the gap is just the gap of qubit version multiplied by n, and this says the gap is just a spin flip of the ground state. So now we know whether delta is the gap for the ensemble version or whether this capital delta is the gap for the ensemble version. So just we should know if we are in the regime that a number of particles is smaller than this critical number or it's larger than this critical number. But you can see that here just this approximation that gap can be determined. The first excited state just is the spin flip of the ground state is valid just when we are above this critical point. But we were interested to know how many of instances really fulfill this criteria that small delta, just spin 1 spin Philip could be the gap. And you can, as you can see here, it's really the number of instances for which a small delta it could not be the gap. It really increases linearly with n, which n is number of particles in each ensemble. So that means for the real ensemble problems that we have a size like in order of 10 to 11, 10 to 12, most of the instances that we have, they are belonging to the regime that the gap is really just the spin Philip. Okay, so now, till now, I just was talking about the problem Hamiltonian. I just briefly make a summary. Just I would say here till here, we just compare the gap and the ground state of the problem Hamiltonian for the qubit version and for the ensemble version, and we saw how there is relation between them. And now we want to talk about the whole spectrum, because you know what matters in any adiabatic evolution is the whole spectrum. So here you see this for some particular parameters of the problem Hamiltonian. Here you can see the full spectrum for the qubit version and for the ensemble version. I would say here that here we consider the spectrum for the case that the number of particles is equal 5. This is the whole spectrum, and this is just a few first state of the spectrum. There is an interesting relation between this one and this one. If you look at, you see there is the same behavior for the first state, and here the same behavior for the last state. Just the difference between this spectrum and this spectrum is that the ensemble version just introduces some extra state between these between the other states. So this, and as you can see, surprisingly, gap does not closes, and it is because I think this fact that gap does not closes just it comes from the fact that ensemble version is scaling with n in comparison with the qubit version. So here I will again discuss about the equivalency of the ground state for the ensemble version and qubit version. For this particular instance that we have considered here, this is a 3-qubit case, and the ground state is -1, -1, -1. So now look at here, let's look at the expectation value of S operators for 3 qubits in the ensemble version. If you look, you see for the first, if you 7 first levels, the expectation values have the same sign with the ground state of this one, and this means that these states are logically equivalent with the ground state. This is important. Why? Because even if during the adiabatic evolution it happens a transition to first a few excited state, it doesn't cause to any error, and they are still logically equivalent with the ground state. So, but now we know a bit about the relation between the spectrum, the whole spectrum, and the ground state and first excited state of the problem Hamiltonian under the mapping that we have considered. But if we want to generally try to calculate the first excited state and the ground state of the ensemble version is quite expensive, because the dimension of the Hilbert scales in this way, while for the qubit state it's like 2 to m. So, but it's good that we know for most of the cases, just one spin Philip is gives us the first excited state, and this helps us to state, okay, the ensemble nature of this mapping help us to use mean field to estimate the gap. So, but how this mean field approximation works here, we just suppose that the ground state is just the product, this is the mean field ansatz for the wave function that says that the ground state just multiplication of all the states when they are all aligned within the same direction. So, and then as an ensemble for the first excited state, we say thus first excited state is just one spin flip per ensemble that gives us a spin wave state. So just know, then we know what is the ground state and what is the first excited state under this mean field approximation. But now to know how this mean field works well, just for some particular instance, we compare the evolution of the gap. Here you can see the evolution of the gap for some particular problem based on mean field, and you can see the evolution of the gap for ensemble case when we have 5 particles in ensemble, 2 particles and 1 particle. You see when we start to increase n, then the evolution really approach to what mean field approximates. And also just to see how mean field works well to approximate how the minimum of the gap scales with the number of particles in each ensemble. You can see, for example, we consider it for different rate of adiabatic evolution, and you can see it starts to converge to the value that this dot values shows what mean field approximates, and these are the real values, and you see that it converges to what mean field suggests. So, but what I was telling you till now, it was just I was considering some particular instances, and I showed you how is the spectrum, how is the gap, and how everything in ensemble version and qubit version are related together. But that would be interesting if we just go through so many instances and try to compare them and see if really what we are saying works for a large number of instances. So then towards this goal, we just generated like 1,000 random instances, and then we just first separated that one for which the gap is what mean field approximates, which means the gap is just a spin flip of the ground state. So we saw that I just here you can see the worst scaling, best scaling, the average scaling for the case that one spin flip is give us the first excited state. And you see the worst scaling says that the gap is just fixed with the number of particles in ensembles. And this is the best scaling. But in average, we can say always the gap, the minimum gap increases with the number of particles in ensembles. But here, for the case, for the instances that if you remember, I told you the proportion of these instances is not really large, and when we increase n, the proportion of such instances really decreases. You see, this is the worst scaling. That means there are some instances for which if we increase number of particles in each ensembles, the gap starts to decreases. And this is the best scaling, and this is the average scaling. There are some instances that the gap decreases for them with number of particles, but still you can see the average improves. So then at least now we know how the story works for if we just go through more instances. Now we want to just know how is the performance of this ensemble version of AQC. So you know the performance of AQC is determined by the success probability that shows us what is the probability of finding the state of the system at the end of the evolution in the ground state. So here we plotted the success with 1 minus success probability, which shows the error, and we show how error scales with the number of particles. Here is for instances that we believe our scheme works, and you can see error decreases with number of particles. Due to the limitation that we had for our simulations, we just have considered a few number of particles in each ensemble, but in reality, it should be like 10 to 11, and you can imagine how much error can decreases based on this ensemble mapping. So we plotted the error for different value of time duration. So here we cannot see that error decreases, but it's because still the time evolution is not enough line. But when the time evolution is enough line, you can see how the error decreases with the number of particles. But for the instances that they are not too much and our scheme doesn't work, unfortunately we can see that for different time evolution, error increases. So as a next step, these are the results when we haven't still included the decoherency. Now let's include the decoherency and see what happens. But before that, the ensemble nature says that maybe decoherency could destroy everything here. But we said before doing numerical simulation, we expected that it's really not the case because as you saw, the mean field it proposes a spin coherent state for the ground state and a spin wave state for the first excited state. And these states are already studied and it has been shown that these states are quite robust against the coherency. So we expected that if even we include the effect of the coherency, it should not destroy the success probability. So again, we plotted the error, which is 1 minus success probability for the instances that one spin flip is the gap, and for the other class of the problem. You can see the error decreases with the number of particles as long as we are in a time window that here I have plotted this plot for the coherency rate of 10 to minus 4. And as long as we are in the time window that the coherency hasn't destroyed still everything, and the adiabaticity is still maintained, you see that error decreases with the number of particles. But this is not the case for the other class of problem, which the gap is just defined with the gap of the qubit version multiplied by n. But I would mention here that always there is a trade-off between maintaining adiabaticity and working within the decoherency time. So that's interesting that we are seeing this mapping even gives us some error suppression. So, but these were like some, we just generated some random instances and we calculated the average of the success probability. But let's go through some specific instances with some specific spectrum and then see what happens there. So we just first of all look at some instance that we know it has a spectrum like this. This instance has a global minimum which all the spins are up, and it has a local minima which all the spins are down. So you know there is a big Hamming distance between local minima and global minima. So we plotted, just I forget to put something here, if I can write here something. So this is the problem Hamiltonian. So here, if we choose just all of the Jij equal, if I is unequal with J, we consider it minus 1, and it's 0 for the other case when I is equal J. And the values of K that I put here, so you see, for example, for this K, here you can see the error start to first of all increases, and then here I put some dot line. it shows where the cross between the small delta and big delta, the crossover between small delta and big delta happens. The points that I call it critical points. So you see error increases, but after this critical point, error starts to decrease. And here again, you can see the critical point here is for k equal 0.2 is here. And you see the error increases, and then once it crosses the critical point, the error starts to decrease. And the same story here for k equal 0.1. You see, it increases before the critical point, but sharply at critical point, it starts to decreases. And we also look at another instance which is called exact cover tree instances, which are these instances are hard in this sense that they have unique solution for the ground state. And you can see even we plotted the error for different time evolution, and you can see the error decreases. So, but still maybe someone argues that, okay, the approximation that you have considered for the ground state says that the ground state is a productive state. Then this means there is no entanglement. But actually, it's not true. There is entanglement, and mean field it's just an approximation. And we explicitly have shown that really there is entanglement. Here we plotted the entanglement in the presence of decoherency for different number of particles per ensemble. And you can see we have entanglement, and when we start to increase, and then this entanglement starts to approach it to some common curve. And this result is somehow consistent with the result that people have shown already, that in such a microscopic scale system, it's possible to still have entanglement even in the presence of the decoherency. So this brings me to conclusion. So what we have shown here. So we found that the ground state of the ensemble version and the qubit version are logically equivalent. And the main feature of the ensemble version is that it just introduces some replica states that they are really equivalent with the ground states, and they somehow make the adiabatic evolution harmless against excitations. And also we have found that mean fields allows us to estimate the gap for some particular instances, and the estimation improves once the number of particles increases. And we saw that we also investigated the performance of the AQC, which means how the error scales with the number of particles, and we saw that it improves favorably with n. We also said that this mean field approach helped us to show that even in the presence of the decoherency, still the scheme works well for some particular of instances. And also, as we have seen, we don't have any necessity to control the qubit individually, so it should not be hard to be implemented in the lab. Okay, thank you for your attention.
Thank you. So, are there questions? Yes, there are multiple ones. So, first.
So, thank you for the talk. Yeah, so how sensitive are the qubit ensembles compared to qubits?
Sorry, how what?
How sensitive?
Oh, I was saying it's sensitive to what?
To noise, basically. To
okay, I was saying that as we show here, based on these plots, when I included the coherency, so you can see the error which is 1 minus the success probability, which shows the performance of the QC. When we include the coherency, we can see that even error is suppressing, and it's quite surprising. But it happens just for some particular instances. And we expected that this happens because what we are seeing that mean fields suggest that the ground state is like a spin coherent state, which it has been shown it's quiet, robust states against the coherency. And first excited state is just a spin wave state, which is still robust against the coherency. If you remember at the first of talk, I said one big problem with using ensemble for encoding is this the coherency problem. But if we choose some smart way for encoding, we somehow are able to circumvent this problem.
Maybe directly a follow-up question. So also, first of all, thank you for the nice talk.
Okay.
If you go back to slide number 23. So
To slide what?
20, yeah, this one.
23.
So if I get the left plot correctly, then the error decreases, right, with the number of qubits I have in my system.
Yes, the error decreases.
Is there any intuition to it? Because normally when you look at the, like for example, at your Hamiltonian, there will be a second order phase transition at the critical point, which means that actually the the minimal energy gap closes polynomially, which means that the computation time increases polynomially. So why is it the other way around in this case?
So no, first of all, you were talking about phase transition. Is that for that type of problems that it's like that we don't have a adiabatic evolution? But here, first of all, I would say that I'm considering some random instances, like 1,000 random instances that the spectrum, they have different spectrums, and then depends on how is the time evolution, we can guarantee if we are in a linear time evolution, then it's easiest to guarantee that always we are in the ground state, and we finally end up with the ground state, and the success probability is large and the error is down. But the point is that here, just suppose there is one particle in each ensemble, which is the qubit version, and you can see how is the error for different times. Yeah. Okay, you see, still we have a good success probability with this average because we have enough line time. Okay, that means in average there were not happening any transition to the excited states. But now the story is that what happens when we start to use these ensemble mappings, and we increase the number of particles in each ensemble, you see that the error decreases. But why the error decreases? What happens? It's surprising, as you are saying, because you saw here, we saw that we have chosen the problem Hamiltonian in an ensemble version in a way that even increasing the number of particles in each ensemble just give us increasing the gap. You see, the minimum gap, in the worst case, is fixed, but in most of the cases, the minimum gap increases. And this is why the error decreases. And all of this comes from the type of problem, the Hamiltonian that we have chosen here. And mostly this 1/n factor in front of these two-body instructions.
Thank you.
No problem.
Any other questions? Okay, sure, why not? Thank you.
So what are the experimental challenges facing implementation of these ensemble
You mean if it's
Hamiltonian?
possible to do the experimental implementation?
Yeah.
So one potential candidate could be just, for example, I'm talking that we can use, for example, ensemble of two levels atom, and then like for using atom chips and just implement this. I explained everything, and what we did is quite general, and it can be implemented in any physical systems.
Thank you.
But if you like, I can give you some references to see how it's possible to do, to realize it in the lab.